All right, so in the first module of today's lecture, we're going to actually work an example of what we talked about in the last lecture. And so that was the equilibrium number of defects, in this case vacancies. We're going to work an example of that question. So I've put the expressions that we had from that last lecture here so you can find them easily. And what I want us to do is calculate the equilibrium number of calculate the equilibrium fraction of vacancies in copper at 1,000 degrees Celsius, and I give you the activation energy QV for copper, and that's 1.44 times 10 to the minus 19 joules per atom. And then for the second part, we're going to calculate the equilibrium number of vacancies per cubic meter at the same temperature, and I give you density of copper and atomic weight just so you don't have to hunt around for them. So just as always, go ahead and pause the video, go to the quiz. These questions will be there, and work through them. And then once you've got your answer, come back and we'll go through each of these parts as a worked example. All right, so let's go ahead and work the first part. So it was asking us to calculate the equilibrium fraction of vacancies in copper at 1,000 degrees Celsius, given the activation energy in joules per atom. So we know from the slides and from the previous problem statement, it gave us the expression for the equilibrium number of vacancies per volume as a function of the total number and then the exponential term. But it's only asking us for the fraction, which means NV over N, as we kind of showed in the last lecture. So for the first part of this question, the first of two parts, all we have to do to get this fraction is then calculate the exponential, right? And so that exponential is minus the activation energy QV. And so that's 1.44 times 10 to the minus 19 joules per atom. And then we have K. K is a constant. It was given in the slides as well. This is 1.38 times 10 to the minus 23. And the units of that are joule per atom K. And so we can go ahead and plug that in, 1.38 times 10 to the minus 23 joule per atom K. And again, you see the K here, and we talked about temperature in the slides. Temperature is important. The temperature given to us was 1,000, but this is in degrees Celsius, right? That's not useful for us, and actually if we put that in, we'll get something else, because you notice that the units here are K, and they do matter when you're looking at cancellation, right? Celsius and K don't cancel out in this type of an expression, so we do need to use not degrees, but the absolute temperature scale of Kelvin. And so to do that, we're going to add 273 or 273.15. Here I'm just going to use 273, and so that's 1273 K as our temperature, and we can plug that in. And so here you see that the K is going to cancel out, the joules per atom are going to cancel out, and when all said and done, the inside of this exponential is going to be minus 8.197 if you want to think about it that way, but the fraction here is 2.75 if we plug all that in, times 10 to the minus 4. Right? And again, this is the fraction of vacancies over the total site. So that's giving a site fraction of how many are vacancies. And so you see here, this is well below, even 1%. And so there are not a lot of vacancies compared to the total site. So it's not like half the lattice sites are vacants. And so that's important in this expression. And one thing to keep in mind is that we're at 1,000 degrees Celsius. This is actually pretty close to the melting. And so we have a really small fraction of vacancies even at the very high temperature, and we know temperature causes an exponential increase in the vacancies. So even at this really high temperature, we have a relatively low fraction of vacancies. So in the next part, we'll calculate the true or absolute value of that per volume, and we'll see if we can glean some more information from that. All right, so let's go ahead and take a look at the second part, which was asking us to calculate the equilibrium number of vacancies per cubic meter at the same temperature of, in this case, we already converted it to 1275 K. So that, and it gives us the density of 8.4 grams per centimeter cube and the atomic weight A of 63.5 grams per mole. So the first part of this expression was, since we are looking at solving this to get the total number of vacancies per cubic meter, which is what we have here, we already calculated the exponential part in the previous part of this question, the first part. And so really we just need n. And so n, as you recall from the previous slides, was defined as Avogadro's number multiplied by density over the atomic weight. And so if we plug all this in, we get 6.022 times 10 to the minus 20, 10 to the 23 plus 23, and that's atoms per mole. So that's kind of our conversion, how many atoms are in a mole, because everything else tends to be on a mole scale. And our density of 8.4 grams per centimeter cubed, and our atomic weight of 63.5 grams per mole. So you see here that the grams are, the moles are going to cancel out, the grams are going to cancel out, and we're going to be left with atoms per volume. In this case, it's going to be in centimeters cubed, so we'll also want to convert that afterwards. But if we just plug this in, we're going to get 7.97 times 10 to the 22, and that's going to be, again, atoms per centimeters cubed. But it's going to be quite a bit bigger if we're talking about a cubic meter. And so when we convert that, again, atoms per centimeter cubed, and our conversion here, we want to convert the cubic meters to, cubic centimeters to meters, and we have 100 centimeters, and that's on the top because we want to cancel out the cubic centimeters, and then 1 meter, and then if we just cube all of that, that'll give us our conversion, and that is 7.97 times 10 to the 28 atoms per meter cube, and that's again equal to n. So that's the first part we need for this expression, right? So this tells us that we have 10 to the 28 atoms per meter cube. That's a huge amount, right? Because we're talking about many moles in this case. So now that we've got now that we've got n, let's go back to that expression that we have up here. And we've already calculated everything that we need. So we know that n is this number that we just calculated. So 7.97 times 10 to the 28 atoms per meter cubed, and then times the exponential, and we've actually already calculated that exponential. Again, inside the exponential was a minus 8,197, and when we do all of that, plug all that in, we get that the number of vacancies is 2.19 times 10 to the 25 vacancies per meter cubed. So again, looking at this, we saw before that it was only 10 to the minus 4 was the fraction, right? So that many vacancies per total number of sites. But in the absolute value here, we see that we still have over a mole of vacancies, right, per cubic meter. So even though the fraction is quite low, the overall number of vacancies is quite high, but we're talking about 10 to the 28 actual atoms per meter cubed. So it's still, again, a pretty small fraction. So whether you look at it as an absolute or as a fraction, it's the same thing, but it kind of shows us just what kind of numbers we're talking about here.